Hey, welcome back to another exam walkthrough. So we're going to be doing some more astronomy questions. This is from Jan 2019, Unit 5, Physics. So the first question says that quasars are thought to be disks of matter moving around black holes. Light received from all quasars shows large redshift. So we know one very important thing, that large redshift means that there's going to be things that are moving away. Okay, moving away. So we can say that option number B and option number D are wrong. Now, are they moving, are they accelerating away? Right? So are these quasars accelerating away from the Earth at large rate, or are they just moving away? Now, one thing you must know is that redshift only tells us that these stars are moving away. It doesn't tell us if these stars are moving away at a high rate or at a low rate. We don't know too much about that. So it doesn't give any indication of the star accelerating away from us or it's accelerating towards us. So the correct option here has to be C. Okay, the next question. The Hubble constant has been determined to be 2.2 times 10 to the power of minus 18, although there is some large uncertainty. So the astronauts found this Hubble constant value, then they found the age of the universe using this value, but there was uncertainty, and the previous value was this much. So they want to know what would the age of the universe calculated from this value would be. Again, they've given you a bunch of options. So what I've done here is I've taken the values and calculated the age of the universe. So I've calculated the age of the universe when the Hubble constant value is this much, when it's 2.0 times 10 to the power of minus 18, and when it's 2.2 times 10 to the power of minus 18, it's this much, so it's 4.54 times 10 to the power of 17 seconds, and then when the Hubble constant value is 2.20 times 10 to the power of minus 18, it's going to be 5 times 10 to the power of 17, and then what I've done is I've found the percentage difference between these two values, and that's going to be 10%. So with that, I can say my option number A and my option number D are wrong because my percentage difference is 10%. So now I can see here that would the Hubble's constant value be bigger or smaller? So they want the age of the universe the age of the universe would be bigger or smaller. So they want the age of the universe when our Hubble constant value is 2 times 10 to the power of minus 18, and we can see that it's a bigger value. With the other value, we're getting a smaller age of the universe. So the answer here would be C. Alright, next one. Cosmologists predict a number of alternatives for the future evolution of the universe. Which of the following statement describes an open universe? So the open universe is a universe in which the density of the universe is less than the critical density, and the universe will keep expanding. Pretty simple. The rest of the stuff is obviously wrong. Correct option is C. So here's the mark scheme for these. You can just check them out. The Hipparcos satellite was the first satellite used to determine accurately the position of stars. Data from more than 100,000 stars was collected by Hipparcos using the parallax method. Now, Hipparcos was actually, he's known as the father of the astronomy. Okay, so we have to really explain what parallax means. So this is basically the change in the apparent position relative to background due to the change in position of the observer. So change in position of the viewed object. Okay, let's write that down there. Alright, so the definition is pretty clear. I could have written it down and taken the time, but I want to explain this a little bit. So you have something here. I think you guys are very familiar with the parallax error. If you view it from different positions, you're going to get a different value. That's the principle of parallax. So you're seeing something change because you're moving around. So there's this apparent change in position of the viewed object. The viewed object doesn't change, it's just that we change position. So I'm going to see it from here and here. I've explained this in the trigonometric parallax video. So that's basically what I've written here. So please make sure you learn this definition and understand it. Okay, so my main thing is you understand here. Okay, right. So next we have is a star is twice as far away from Earth as star B, so star A is twice as far. And then it says, what would be observed when the trigonometric parallax is used to determine the distances of these stars? Alright, so now we can see that here I have the sun, okay, and here I have Earth. Now what's going to happen, I'm going to measure the change in the angle from this position, and then I'm going to measure it from this position, okay? And then for the other one, I'm going to do the same. The other star is at a bigger distance. This is star A and this star B according to the question. And then for the other star as well, I'm going to do the same thing. I'm going to measure its angle, the change in angle from two different positions. So we're going to measure it in Jan, and then we're going to see it in June. Okay, so what's the first point that you'll get, first mark you'll get, is you will say that when the star is seen between the interval of 6 months, okay? The star is seen from Earth in an interval of 6 months, and you will see that the angular, the parallax angle will be half. The reason is, you can see this is the formula of the trigonometric parallax. Tan theta is equals to 1 by d, where 1 is the astronomical unit. So 1 astronomical unit. Now, if the distance doubles, then the tan theta will half, and we know tan theta is approximately equals to theta. So we can say that the parallax angle will therefore half. Okay? So that's the answer to this question. So that's going to give you the second mark, and that's going to give you the first mark. Okay, now it says it was intended that Hipparchus would orbit the Earth directly above the equator with a period of 24 hours. So it would have the same period as Earth, which means as the Earth rotates 360 degree, so the satellite also will complete its one full cycle in 24 hours. Which means that if the satellite is here, it will always be at relative rest. Okay, at relative rest with respect to Earth. Okay, I have explained this a bit more where we have gone through the geostationary satellite. So this is the geostationary satellite. Okay, so whenever you measure from here, okay, the satellite, and you see, okay, where it's at, so it will always be at this position. You will be rotating, so if you're here, the satellite will always be here. If you're at this position, it will be this. So it's kind of like rotating with you, right? So the first point you can write is that the satellite is always directly above you. So it is at relative rest. Okay, that's the first point. So number two, because of this, because it's directly above you always, it is easier to communicate with the satellite. Okay, so the satellite will always be at the same position, so you can easily communicate and share the data with it, and that's why it's better. So 1 point for this and 1 point for this. So next they've given us a Hertzsprung-Russell diagram for a star cluster in our galaxy, and they have told you that we have a star cluster that has the main sequence stars, and then the red giant stars, and then they tell you to complete the scale on the temperature axis. So what you want to do here is you want to complete this value here and this value here. So remember, there are two things. One, this is a reverse scale, and second, it is a log scale. Okay, which means if this value here is going to be actually 5,000, then this value here will be double. So you're going to write 10,000 here, and then the value on this side would give you 2,500. Okay, so that's what you have to show. So 1 mark you get for showing the reverse scale, and the second mark you get for showing that log scale or power scale. Okay, and then next thing, it says explain how we know that red giants are large in size, right? So red giants are right around here. You can see they have high luminosity and low temperature. So first we get right that red giant stars have, first thing, they have high luminosity, and second thing, they have low temperature. And we know the formula of luminosity is equals to the Boltzmann constant, area, and temperature to the power 4. So because of this, we can say that the temperature, if it is going to be low, and if the luminosity is high, then their area will be large, so they will be having a large size. Okay. So next it says, explain how this diagram shows the star cluster is neither very young nor very old. So it's neither very young or nor very old. Now, first thing you could say, now listen carefully, most of the stars you can see are in this main sequence. Okay, so you will write most of the stars are in main sequence. Now we know what happens. The star goes from this position in the main sequence cycle. In the star cycle, it goes from main sequence to the red giants. Okay, and then from there, it's going to go into the white dwarf right here. So it's going to go from 1 to 2 to 3. Now, if the star is old, then it's probably, if the star is very old, you'll find a lot of stars here. If this star cluster is old, you're going to find a lot of stars here. Now, if the star cluster is not very old, which means like then you would find no stars here. Okay, so we can see that the stars are not very old. If they were very old, you would find a lot of stars here as well. Okay, so most of the stars are in main sequence. No stars are in the white. No stars are white dwarfs. So dwarfs. Okay, so they're not very old. Now I will write this much later as a point. Okay, let's put this down. So the next thing you would write about is that you have a little bit of stars that are in the red giant. So there are some stars which are red giants. So these stars cannot be very young either, because there are some stars that have evolved into red giants. Okay, and then those red giants became, they should have become white dwarfs, but we can see there are no white dwarfs. If there were, we could say, okay, these stars can be very old, but there are no white dwarfs, so not very old either. So not very old, not very young. Okay, these are kind of like the middle-aged stars. Okay, so that's going to give you 1 point for this, 1 point for this, 1 point for this, and 1 point for this. Okay, so most of these questions were pretty simple that we have gone through. Besides, maybe a few could be tricky, like this one is a bit out of spec as well. You don't have to really know about all of this. It's more about thinking in exam pressure. So just get used to these things and really get your critical thinking on. And I'm just going to show you the mark scheme and examiner report.